my pleasure to welcome you the second day of conference. To start our day, we have a plenary talk of Professor Levitas from Iowa State University. The talk is new rules of coupled severe plastic deformations, phase transition, and construct evolution of the time ratio. Professor Levitas, the floor is yours.
Thank you, Mr. Chairman. And I would like first to thank the organizer for giving me such opportunity, and also my collaborators and funding agencies. I will start with introducing more or less a new concept of plastic strain-induced phase transformations versus traditional pressure-induced phase transformations, which require completely different thermodynamic and kinetic description and experimental characterization. I will give examples on our in situ experimental finding for several material systems. Then we'll formulate practically first rules for strain-induced phase transformation and microstructure evolution under severe plastic deformation. First present four-scale theory and from atomistic to macroscale behavior of sample. And this part of theory will be used in combination with experiment to extract material properties and transformation kinetics from very heterogeneous fields in a sample. And also will give application to resolving puzzles of deep focus earthquake mechanism. And at the end, I will show that the microstructure, initial microstructure, plays significant role in traditional plastic strain-induced phase transformation, and it evolves significantly during, it plays significant role in traditional study under hydrostatic loading, and it significantly changes during hydrostatic loading, and also will find some new rules. So processes involving severe plastic deformations and phase transformations at high pressures are widespread in science, technologies, and natures. And examples are material synthesis under static and dynamics condition, mechanochemical material synthesis, producing nanostructured materials by severe plastic deformation, processes in diamond anvil cell and rotational diamond anvil cell, various surface processing, friction, various military and geophysical applications, and even mechanochemical region of life beyond Earth. And each high pressure lab has diamond anvil cells, so sample within gasket or without gasket is compressed by two diamonds, and modern technologies are used to probe sample. And what we are doing differently after compression with twist one of anvils, superposing large plastic shear. And this changes everything. To some extent, this is similar to high pressure torsion originated by Bridgman. And there is now very large material community which uses routinely high pressure torsion to produce nanostructured materials. But advantages here is that due to diamond anvils, we can measure everything in situ and resolve along the diameter, which is very important because all fields are extremely heterogeneous. And also much higher pressure can be reached. And yes, rotational diamond cell I brought from my group in Kiev, Ukraine to US in 1999. And this was initiation of study of plastic in situ study of plastic strain-induced phase transformations. And currently we use two our old rotational diamond anvil cell and two new dynamic rotational diamond anvil cell for small strain rates and just started for large strain rates. Main effect of plastic straining is that it drastically reduces phase transformation pressure. And you see here results, for example, for boron phase transformation in boronite and zirconium, it's by factor of 8 to 10. So order of magnitude, and the largest reduction was obtained for phase transition for graphite to cubic diamond. It's 2 orders of magnitude. And the hydrostatic condition, diamond appears at 70 GPa, if at all, and we obtain it at 0.7 GPa. So if this could be scaled up, this would be new technology of defect-induced diamond synthesis without temperature, without catalyst, and practically without pressure. And also it has, this result has geophysical implication because it changes completely mechanism of possible appearance of microdiamonds in cold earth crust. Usual hypothesis was that this material moves subduct to high pressure temperature zone where diamond traditionally appears and uplifts back. Now this could diamond synthesis could happen directly in cold earth crust in shear bands where actually they were found. Infinities here means that, for example, silicon-3 and gamma spinel don't appear under hydrostatic loading at all, but we obtain them at relatively small pressure here and 16 GPa here. Also, plastic straining leads to new phases, which were not obtained under other conditions. And example, we obtained, for example, reversible phase transition to new high-density amorphous phase of silicon carbide at 30 GPa and large shear. And under quasi-hydrostatic conditions, even at 135 GPa, nothing happens. And amorphization is considered a mechanism of damage in armor ceramics. So it's very important, and since it's reversible, the only way to detect this is in situ study. Also, we recently revealed the new super hot disordered phase of boronitride. You see it scratches diamond, and even cubic boronitride cannot scratch diamond. And problem is that classical thermodynamics, even if you substitute pressure and volumetric strain with 6 components of stress and strain tensor, cannot describe order of magnitude of this phenomenon. That is why we develop 4-scale approaches. And at atomistic scale, our goal is to find phase transformation criterion, not phase equilibrium, but phase transformation criterion on the action of all 6 components of stress tensor. And due to large number of combinations, this seems to be impossible, but we are working also at continuum scale. And we develop over years phase field approach to phase transformation. And within this phase field approach, we derive analytically equation for phase transformation criteria. And then our goal is simply, we need just to check it. And that is how it looks under such loading. And key point is that it's linear in stresses. That means that in stress component space, this is plane. Then we twist this plane until it's visible like line, and you see dots here are results of molecular dynamics simulation, and here results of DFT simulations. So this strongly confirms our prediction and also allows to determine 2 material parameters. When we add 3 components of shear stresses, we have additional term here, but again, deviation from prediction in MD and DFT is within 5%. So right now, that means that we have a simple analytical expression for phase transformation criterion for silicon 1 to silicon 2 on the action of all 6 components of stress tensor. And this is well beyond of what was known in literature, mostly for 2 components and very few works for 3 components. And we also developed 5th degree elastic energy based on DFT simulation, and then you see comparison of stress strain curve at various complex loading, a very good comparison with DFT, large strain even beyond initiation of phase transformation. But this was ideal material without defects. All material have defects and they play a crucial role in this phase transformation. But first, I would like to mention that before appearance of this paper, there was not understanding in high pressure community that there are 2 completely different types of phase transformation. So traditional pressure-induced phase transformations under hydrostatic pressure starts at new pre-existing defects, which represent stress concentrator, and because there is limited number of defects, so one needs to increase pressure to run phase transition. And here we introduce concept of plastic strain-induced phase transformation under high pressure, which occur during plastic flow. and then acute at new defects, permanently generated plastic during plastic flow. So there is no saturation of defects here, and these transformations represent defect-induced phase transformations and require completely different thermodynamic and kinetic description and experimental characterization. And the only existing defects which can describe order of magnitude of reduction in phase transformation pressure is dislocation pileup. And first, we developed simple model, analytical model for nucleation and dislocation pileup. And then over years, we developed much more sophisticated phase field approach. It took more than 10 years for interaction between phase transformation and discrete dislocations. And let's consider material with properties close to properties of silicon. So phase equilibrium pressure is 10 GPa under hydrostatic condition. And if you introduce single dislocation, phase transition occurs at 16 GPa. Now let's consider bicrystal under compression and shear. So dislocation nucleate at grain boundary and pile up against grain boundary. And key point is that all components of stress tensor here are proportional to number of dislocations in a pile up. And it can be huge, you see 10 and even 100. So we have here huge stress concentrator for all components of stresses, and that is where our atomistic phase transformation criterion is satisfied. And you see nucleation, and this occurs at pressure average over the volume equal to 1.2 GPa. And this is conceptual proof that dislocation pileup can indeed reduce phase transformation pressure by more than order of magnitude and even almost order of magnitude below phase equilibrium pressure, so deeply in the region of stability of low pressure phase. Then with increased shear, you see coalescence and quite large amount of high pressure phase, but here we neglected dislocation activity in right grain. When we include this, you see that much smaller amount of high pressure phase. That means that plasticity plays dual role. It promotes phase transition by creating by creating stress concentrators, but it also suppresses phase transition by relaxing this stress. But we found various combinations of normal and shear stresses when solution without dislocations and with dislocation are approximately the same. So this is controllable, and we summarized our nanoscale results as new possible routes for defect-induced material synthesis based on generating stress concentrator. Now, in this paper, I made many predictions, and most of them were confirmed by experiment. One was exactly opposite to what we later observed. And I did actually nothing wrong, so I used classical SLB model for dislocation pileup. And concentration of all stresses at tip of dislocation pileup is proportional to shear stress and the length of dislocation pileup. Length of dislocation pileup is traditionally taken as fraction of grain size. And that means that the larger grain size, the larger stress concentrator, and the smaller phase transformation pressure is. And this is exactly opposite to what we observe in experiment. Well, it's not shame to be full, but a shame to remain full. So we have to correct this, right? And in years, we realized using our phase field simulations, molecular dynamic simulation, and also concurrent atomistic and continuum approaches, that dislocation under our high shear stresses, dislocation pileup is localized at grain boundary. So it's much smaller than grain size, and it's independent of grain size. And this is like super dislocation. And when we developed theory of nucleation at super dislocation and took into account grain size dependence of yield strength, this is direct and reverse whole page relationship, put everything together, we predicted relationship between yield pressure, grain size dependence of yield strength and minimum pressure for strain-induced phase transformation. So in a region for direct whole patch effect, when yield strength grows with reduction of grain size, we predicted that phase transformation pressure should reduce. And indeed, for Micrometer silicon particles, phase transformation pressure is 2.5 GPa. For 30 nanometer particles is already 0.3 GPa. And in the region of reverse hole patch effect, when yield strength reduces, we predicted that the phase transition pressure should increase, and indeed for 30 nanometer particles, it's already 4.9 GPa. So this is very strong confirmation of dislocation pile-up based mechanism and first correlation between grain size dependence of yield strength and minimum pressure for phase transition. And this is very unexpected because under hydrostatic conditions, phase transition pressure grows with reducing grain size. And also look at these numbers. Under hydrostatic conditions for 100 nanometer particles, phase transition pressure is 16.2 GPa, and under plastic flow, it's 0.3 GPa, so 54 times reduction. And what is also important, it's the same 0.3 GPa under compression in diamond anvil cell and under torsion and rotation of diamond anvil cell. So if microstructure is ready, then result is independent of straining path. And we also measure evolution of crystallite size in each phase during loading. And here I put numbers for crystallite size at the beginning of phase transition. And the same rule can be formulated in terms of crystallite size instead of particle size. Problem is that TM Fox says that we don't see dislocation pile-ups in nanograined materials. So this is not supported. But the point is that in our simulations, after loading phase transition, when we release stresses, we also don't see dislocation pile-up. They disappear. So they should be detected in situ, and nobody can help us to find how to do this. But recently we received very strong confirmation of strong stress concentrator. And you see, we measure pressure in each phase. And at the beginning of phase transformation, pressure in silicon 2, in high pressure phases, silicon 2 and silicon 3 is 5 to 7 GPa larger than in silicon 1. And this is despite 22% of volume reduction. And this is strong direct confirmation that there is very strong stress concentrator, and the only way to obtain it is due to dislocation pile-up. And this is consistent because for 30 nanometer particles, where dislocation activities are suppressed, increase in concentration and pressure is just 1.4 GPa. So I believe this is the first direct confirmation that plastic strain-induced phase transition occurs due to strong stress concentrator. And to scale up our simulation results, we developed completely different microscale phase field approach. It's you see here, red is evolution of high pressure phase. This is dislocation evolution, and we can consider large polycrystalline sample, and also despite the different orientation of grains with respect to shear, almost complete phase transition is obtained under almost complete, quite small shear. Here we also resolve not only just low pressure phase, high pressure phase, but also crystallographically equivalent morphic variants, their evolution. And we obtain distribution of volume fraction in each grain. It's very heterogeneous than average over the sample characteristics. So now we know how volume fraction varies, pressure varies, shear stress varies, and this is basis for development of macro scale kinetic for strain-induced phase transformation, but I will discuss this later. Also, we obtained several other interesting results for silicon system. For example, for 30 nanometer particles, silicon 2 does not appear under hydrostatic condition at all, but we obtained it at 4.9 GPa. Then under hydrostatic loading, silicon 3 also does not appear during loading for any particles, but we obtained it with torsion at 0.6 GPa. then nobody could retrieve silicon-2 after pressure release because it transforms to different phases. But different phases. But due to plastic straining, we could retrieve silicon-2 and even uniform silicon-2 without any poor silicon-2. And also, nobody could obtain reverse phase transition from silicon-2 to silicon-1 because other phases appear. But because we obtain silicon-2 at low pressure, then other phases are suppressed and we return it to silicon-1. Also, there is problem to obtain silicon, single-phase silicon-3. And for example, one of technologies is quenching from 14 GPNs 900 Kelvin over 3 days. And just by accident, because we have a long diameter, 60 points, and just checking some points at some loading, we found that we obtained uniform single-phase silicon-3 by quenching from 11.6 GPa and in quite large region. So you see that with plastic straining, there is possibility of manipulating of synthetic paths. And this opens new opportunity for economic material synthesis. And also two more potential applications of these results is that observed very low phase transformation pressure warns that some phase transformation may occur in NEMS, MEMS, during contact interaction, during friction, and they should be avoided. And also silicon-1 and also is brittle, and during polishing cracks, nanocracks appears near surface, and they are removed by chemical mask. That is why researchers invented ductile regime of machining for silicon, for ceramics, and they choose such parameters of tool and load that they initiate phase transformation. And usually this is to more ductile silicon-2 or amorphous phase. And then this more ductile phase is removed without nanocracks. But problem is that in all simulations and design, transformation pressure here is like 10 GPa. And we obtain this phase transformation under 0.3 GPa. So there is significant room for improvement of simulation and optimization of this process. Next topic is strain-induced phase transformation in zirconium. And well, there is general problem. Main basic problem in studying plasticity, microstructure evolution, and phase transformation is that they depend not only on 5 components of plastic strain tensor and pressure, which is already a huge amount of independent parameters, but also on entire plastic straining path. For example, if you produce compression and then shear, or shear and then compression to the same strain, or any combinations of shear and compression, so other losing, results are different. So this means that there are infinite number of loading paths, and this leaves little hope to find any general rule. But actually, we develop using in situ method, which we develop and use, and theoretical approaches. We found first quite general rules in this field, and namely that after severe plastic straining, first minimum pressure for plastic strain-induced phase transformation, pressure-dependent yield strength, crystallite size, and dislocation density in both phases are getting steady. So they don't change with further plastic deformation and independent of plastic strain, tensor components, and entire path. And during phase transformation, crystallite size and dislocation density all are unique function of volume fraction only, and also are independent of plastic strain path, and even pressure. And this is a huge amount of information, and which simplifies drastically theory. And I will show now this in more details. Experiments are performed on strongly predeformed zirconium. That means that we produce multiple rolling until hardness, dislocation density, and crystallite size are getting steady. So, and don't change anymore. That means we exclude them from independent parameters, and this simplifies study drastically. And we produce compression and torsion, and this is kinetic equation for plastic strain-induced phase transition, which we derived micromechanically. Time is not parameter, so accumulated plastic strain is time-like parameter, and it depends also on ratio of yield strengths of phases. And this is pressure plastic strain loading path. This equation is shown as line is here volume fraction versus some weighted plastic strain. And here are 3 loading passes, and all experimental points are very close to our predictions. That means it's we confirm our kinetic equation and determine material parameters. Here is evolution of pressure distribution and volume fraction distribution along the sample. Everything is determined by in situ XRD. And you see pressure for initiation of phase transformation is practically independent of radius. But at each point here, we have different plastic strain tensor components and plastic strain paths. In particular, at the center, we don't have shears at all. And with increasing radius, shears increase. And then independence of radius means that minimum pressure for plastic strain-induced phase transformation is independent of plastic strain tensor components and entire plastic straining path. That is what I announced before. And immediate consequence is that strain-induced phase transformation under compression in traditional diamond anvil cell and in torsion in rotational diamond anvil cell don't fundamentally differ, and they can be studied by anyone in traditional diamond anvil cell if microstructure is, well, already prepared. So if we reach steady state of microstructure, then we will see similar strong effect. Of course, rotational diamond anvil cell has advantages that it controls independently pressure and plastic strain, and it also allows produce much larger plastic strain, and not only start but complete phase transformation under low pressure. And friction plays a crucial role in high pressure research because it determines pressure distribution and maximum possible pressure. And usual assumption is that it's equal to yield strength and shear. And this is used in method to find pressure dependence of yield strength and shear. Because we can calculate, determine all stresses, we found that actually friction stress is even less than half of yield strength and shear. That means that known methods have significant error. And that is why we suggested to use diamond with rough surfaces. And so instead of asperities of 10 nanometers in standard diamonds, we use 30 nanometers in rough diamonds, and they were prepared by polishing by Rainer Böhler or by laser ablation by Sergei Antipov for us. And indeed, we found that shear stresses reach maximum value equal to yield strength in shear. And we advanced slightly known equilibrium equations that pressure gradient is proportional to pressure-dependent yield strength divided by local thickness. We took into account heterogeneity along the thickness. That is why we obtain additional term. Then pressure distribution we measure with X-ray, thickness with X-ray diffraction, this thickness with X-ray absorption. And you see pressure distribution points, experimental, and all of them are described by this simple pressure dependence of yield strength, which is independent of plastic strain, independent of plastic strain path, and does not contain any information about anisotropy. But at each point of sample for different lots, we have different components of plastic strain tensor, different plastic strain path, and materials acquires anisotropy. So that means that after severe plastic deformation, material behaves as perfectly plastic, isotropic, and strain path independent. This is the rule for plastic flow. But there is contradictions here that everyone knows that this yield surface depends on plastic strain path, and you see it varies in stress space. This from this, and this. And the material is getting anisotropic because it acquires texture. So how it can deform like isotropic? And to resolve this contradiction, we introduce additional limit yield surface, which is fixed and isotropic and independent of plastic strain and plastic strain path. And during loading, stress vector and this traditional yield surface reaches our limit yield surface and then moves along. And that means that material deforms like perfectly plastic, isotropic, and independent of plastic strain and plastic strain path. So this resolves contradiction. And this perfectly plastic state corresponds to steady microstructure. So you see, we measure microstructure, crystallite size, the same for dislocation density. It's very heterogeneously initially, but then it's getting independent of radius. And that means that it's getting steady, independent of plastic strain and plastic strain path and even pressure. And during phase transformation, you see messy curves here. And but when we plot all this data versus volume fraction of high pressure phase, we obtain single curve. That means that during phase transformation, crystallite size depends only on volume fraction of high pressure phase and is independent of plastic strain, tensor, plastic strain path, and pressure. And this is also, these are first rules in the field. And this rule has very important practical applications. You see here, even at 14 GPa and corresponding large plastic strain, here it's only compression. We cannot reduce crystallite size below 60-40 nanometers. But during phase transformation in pressure range of 0.7 to 3 GPa, you see crystallite size varies from 5 nanometers to 60 nanometers. So phase transformation is much more economic way to reduce crystallite and grain size than just severe plastic deformation under high pressure. And here there is possibility to obtain nanocomposite with optimal properties. The same exactly is true for dislocation density. After phase transformation here, it's independent of plastic strain and plastic strain path and pressure. And during phase transformation, it's also independent of all these parameters and depends solely on volume fraction of high pressure phases. So, and this plethora of results was obtained in a single experiment because we collect a lot of points along the diameter of sample, and thus transforming the main challenge, strongly heterogeneous fields, into great opportunity of generating big data for further post-processing. Well, problem is that, yes, first rough diamonds, rough anvils actually significantly change character of plastic flow and phase transformation. And you see, actually, we have 3 steady states now. So after rolling, we have such value of dislocation density and crystallite size. And with rough diamonds, dislocation density is essentially larger than with smooth diamond, and crystallite size is essentially smaller than with smooth diamond. And that is why phase transformation pressure with rough diamonds is 2 times smaller than with smooth diamond. So it's quite strong effect, but then we get problem because we have multiple steady state, and we claim that each of them is independent of plastic strain and plastic strain path. That means we have several steady yield strengths and several yield surfaces. So how, and this is contradictory, how it's possible that behavior is plastic strain path independent. So that means that this is new key problem, and I don't know solution, but problem is that for which classes of strain passes material behaves according to each steady microstructure and yield strength, and for which passes of for which strain passes a jump from one steady state to another. And this is unsolved problem. If without solution, we don't have consistent theory for severe plastic deformation. If we solve it, we also will be able to explain why different severe plastic deformation technologies like ball milling, high pressure torsion, equichannel pressing produce different steady grain size. Well, to develop quantitative science, it's not sufficient to talk about stress tensor and plastic strain tensor, but they should be determined, and they are not measurable. And even parameters which we can measure, which I showed you, they are average over the thickness of sample. So in this situation, we suggest we develop combine experimental, analytical, computational approaches to extract material information and all fields from heterogeneously deformed sample. So we develop model of plastic flow and phase transformation, then solve problems and find all fields and then feed to parameters which we can measure in experiment. And from this fitting, we determine all parameters. But there is also a problem with experimental measurements. So how we determine pressure, we measure volume of unit cell and use hydrostatic equation of state. That is what many are doing. But problems are that first equation of state and the hydrostatic and non-hydrostatic conditions are quite different. And second, with axial diffraction, only planes which are close to be parallel with beamline contribute to X-ray pattern. So Z component of strain and corresponding stresses practically don't contribute to X-ray pattern. And that is why we take from experiment only distribution of radial and hoop elastic strains and don't use equation of state. And so after performing this procedure, we found at the initial stage distribution of friction stresses, and you see indeed they are much lower than yield strength and shear. And then we found rule how they depend on friction rules for alpha phase, omega phase, and for mixture. I will not go in detail. This is our model, the mechanical part of model. Phase transition part will come later. And one of result is that if you don't do any simulation and just use traditional method of measurement based on equation of state, minimum pressure for phase transformation is 1.6 GPa. When we solve our problem and feed to all experimental data, actually changes quite significantly, 2.7 GPa. So there is significant error in existing method of determination of pressure under non-hydrostatic conditions. This is our advanced kinetic equation for plastic strain-induced phase transition. I already discussed this part, but now we have more opportunities. We introduce more parameters. So now 6 independent parameters. And after fitting to experiment, we found all these parameters, and actually 2 of them are not necessary. So we can do this with 4 parameters. And you see symbols are experimental data for low and high concentration, volume fraction of phases. And you see quite good correspondence. So maximum difference in volume fraction is 7%. And that means that this is very good within error of experiment. And this equation depends only on accumulated plastic strain, and it's independent of plastic strain tensor components and entire path. This is also new rules, which is more strict because now we use fields in entire sample. We also have good validation for sample thickness profile and for elastic strains. And now, because we have a well-validated model, we can calculate all components of and all tensorial, all fields which are in sample. And this is example of evolution of shear plastic strain, radial plastic strain, axial plastic strain. So this is in alpha phase, this is in mixture, and this is quarter of sample. And this is in omega phase. So key message, it's extremely heterogeneous, even along very thin thickness. But it's heterogeneous, and this is important. Also, evolution of volume fraction, it's quite heterogeneous at the beginning. Accumulated plastic strain pressure. So now we know all fields, and we can use this big data to extract information about evolution of extract rules on evolution of microstructure and phase transformation on this plastic deformation. I already told you new rules on the severe plastic deformation, but we need to do this also for intermediate values. And this is much more sophisticated. Now, next topic is a new mechanochemical mechanism of deep focus earthquake. Deep focus earthquakes occur at such depths in such pressure and temperature ranges, and they are generally assumed to be caused by shear bending due to phase transformations from metastable subducted olivine to spinel in this region, in transition zone. But there are many existing puzzles, and two of them are what are the mechanisms for jump from geological to seismic strain rate. This is 18 orders of magnitude. And also, how does metastable olivine, which does not transform over a million years, suddenly transforms over seconds? And we introduce several new concepts and resolve this and several other puzzles. And main point is that we treat phase transformation from olivine to spinel as plastic strain induced, not pressure induced and temperature induced, but plastic strain induced, which was never done for any geological material. And that means that we have to use our kinetic equation instead of traditional kinetic, strain-dependent kinetic, instead of traditional pressure and temperature-dependent kinetics. And according to our kinetics, it's in the, which I discussed, it's independent of time. That means that the transformation rate is proportional to strain rate. You see, delta T can be excluded from both sides. And that means that if you will show that plastic strain rate is increased by 18 orders of magnitude, transformation rate will be increased proportionally. So now we need to show how transformation rate, how plastic strain and plastic strain rate increase. And we found simple analytical solution for phase transformation in a shear band. And this is so-called shear strain due to transformation-induced plasticity, or TRIP. TRIP occurs due to volume change under applied shear stresses. And it's proportional to volumetric transformation strain and such combination of shear stress over yield strength and shear. And in shear band, shear stress is equal to yield strength and shear. So we have zero here and singularity. Plastic shear tends to infinity in shear bands during phase transformation. And this explains huge shear strain observed in nature in transformation shear bands. And such huge strength produces huge strain rate and corresponding connected transformation rate. But even more, so what happens that phase transition produces trip shear, but this is also plastic strain. And this plastic strain produces phase transformation again. Again, phase transition produces trip shear produces again phase transformation. So we have positive mechanochemical feedback, and then blown up transformation trip heating process. And when we put all this in equations, we obtain quantitative resolution of all puzzles. Quantitative, I mean within order of magnitude. Resolution of all puzzles. This was poor theoretical paper, but now we have some conceptual experimental confirmations. So gamma spinel does not, at room temperature, does not appear at any pressure on the hydrostatic loading. But with plastic shear, we obtain it within tenths of seconds. And it was obtained in pressure range from 15 to 21 GPa, relevant to phase transformation. And this is conceptual proof that plastic straining indeed can accelerate drastically phase transformation, even at room temperature. And also we found first rules here that phase transition pressure reduces with increased plastic straining and corresponding increase in dislocation density and reduction in crystallite size. And also we found that crystallite size in olivine and spinel after severe plastic deformation are getting steady and independent of plastic strain path and pressure. And also spinel is weaker, significantly weaker than olivine. That means that we can expect strain localization, and indeed in our finite element simulation, we found appearance of transformation shear bands. And that is exactly what we need for earthquake. We need appearance of transformation shear band, and they are here, they produce when we average over the thickness volume fraction, it oscillates, and similar how it oscillates here. You see, and this is quite strong confirmation of our theory for new mechanism of deep focus earthquake. And you know, this solution for shear bands, actually in a simplified two-dimensional version, I found it long time ago. And it has many other applications. For example, it describes acceleration of chemical reaction and also reactions in shear band, and led us to discovery of RIP, reaction-induced plasticity. It's very similar to transformation-induced plasticity due to volume change under non-hydrostatic condition. Here, it explained appearance of shear transformation band in Fullerene and the plastic deformation. Problem is that high pressure phases in Fullerene are much stronger than low pressure phase. So why shear bending occurs? It's impossible based on traditional theory. But due to transformation-induced plasticity, we obtain this. And the same we obtained to explain the results for phase transformation in cubic boron nitride. Well, last point last topic is I would like to show that plastic deformation strongly affects also behavior under hydrostatic condition, including equation of state, phase transformation, and microstructure evolution. Microstructure significantly evolves during hydrostatic loading, even without phase transformations. And this should be taken into account. So we compare cold roll zirconium and anneal zirconium. And you see transformation curves. Blue is cold roll. And for pre-strained zirconium, transformation starts at 0.8 GPa earlier, but actually ends later than for annealed sample. And it's quite significant difference. And this explains partially big scatter in transformation pressure and transformation kinetics, which is observed in literature from different groups. So each one obtains own sample with different prehistory, which is unknown. And if not characterized, then this goes to scatter because the microstructure for each sample is different. Also, even if you anneal sample, one of most popular methods to make sample for diamond anvil cell is to scratch tip from big chunk of material. But scratching is severe plastic deformation. So you already produce nanograin material. And each one scratches in own way, right? So it's not repeatable. That means that microstructure should be characterized at the beginning. And that is how it evolves during loading. So in alpha phase, for the domain size or crystallized size, for anneal sample, it reduced significantly during loading and slightly reduces for pre-strained sample. And during phase transition, domain size significantly grows, but then also reduces with pressure, and it's larger for anneal sample. Dislocation density significantly increases in alpha phase for pre-strained sample, and it reaches 10 to 15 over meter squared. This is value which people also try to achieve on the high pressure torsion. But here it's just hydrostatic loading of preliminary plastically deformed sample at normal conditions. Then during phase transformation, dislocation density is not inherited. It drops drastically. And then after phase transformation, it grows. And it grows more significantly for plastically pre-deformed sample. Then when we plot all data versus volume during phase transition versus volume fraction of high pressure phase, it appears that curves for annealed and plastically deformed samples are practically in omega phase, practically concise. And this is first rule for microstructure evolution due to pressure-induced phase transformation, that dislocation density, domain size, and average microstrain is a function of volume fraction of high pressure phase only, and independent of prior plastic strain deformation and pressure. And interesting that during unloading, domain size does not change for both samples. So effect of pressure is irreversible. But dislocation density does not change initially, but then drops significantly for pre-deformed sample and slightly for annealed sample. And what is interesting that final dislocation density for annealed sample is higher than for plastically pre-deformed sample. So actually pressure in phase transition cycle produces higher dislocation density than preliminary plastic deformation in the same site. And the equation of state also significantly differs for alpha phase and practically does not differ for omega phase, because microstructure differs much more significantly for alpha phase than omega phase. So this supports my statement that everything depends on microstructure, and it should be characterized even on the hydrostatic experiments. And change in dislocation density on the hydrostatic condition means plastic flow on the hydrostatic condition. What was neglected, but it's here. Well, and in remaining -2 minutes, right, I will discuss conclusions. So plastic strain and defected use. Yes, that is what. Yeah, plastic strain or defect-induced phase transformation during severe plastic straining under high pressure is a relatively new field of fundamental and applied study with various applications for economic material synthesis of nanostructural phases, nanocomposite, for surface processing, friction, for geological processes, various military applications, and so on. And because it has so many applications, I hope that many high pressure researchers will jump to this field. And as I mentioned, there is a very large community, producing nanostructured materials by severe plastic deformation under high pressure, mostly by high pressure torsion. But they are mostly interested in applied aspect, and they practically don't do in situ study, only very detailed post-mortem study. And don't have corresponding theory which we have now, and they are very interested in this stuff. So I belong to this community last 5 years, and they also last year on biggest conference they gave me plenary lecture because they are very interested in situ study, and that is where high pressure community which does in situ study routinely can contribute significantly. And I presented various important new phenomena and new rules for in situ study for various material systems, for evolution of microstructure, for plastic strain-induced phase transformation, and similar rules also under hydrostatic conditions. Presented four-scale theory from atomistic through nano and microscale phase field approaches to macroscopic behavior of sample. And macroscopic model was used to develop coupled experimental, analytical, and finite element models for extracting material properties and determination of fault and zorial and all fields in strongly heterogeneously deformed sample. And also results were applied to resolve puzzles of deep focus earthquake mechanism, and we have also some conceptual experimental confirmation. And as I mentioned, we found some rules of microstructure evolution and effect of preliminary plastic deformation or initial microstructure on processes under hydrostatic conditions. And the last statement is that we urgently need postdoctoral researcher to continue this work. Thank you for your attention.
Thank you very much for the very nice talk. Now it's time for questions, comments from the audience.
Yeah.
Very nice talk. I have
Thank you.
I had a problem with pressures. When you talk about hydrostatic conditions, so pressure is fine. But if you have gradients, and we studied this with Ruby, if you have gradients, the microscopic local pressure at the contact is quite different.
Of course.
So when you say pressure, that mechanism has a lower transition pressure, I question that.
Okay. Well, I agree. There is indeterminacy, and I showed this indeterminacy. First, we measure pressure not with Ruby. We measured this before, but we measure pressure directly with X-ray. And as yeah.
This is small.
What? Oh, you mean local? Okay, yes, we resolve, of course. But that is what we resolve by multi-scale theory. So first we determine macroscopic pressures, macroscopic field, right? Which are, let's say, average over the size of X-ray beam. Let's say a few micrometers to 10 micrometers. This is level where we determine macroscopic parameters. And for these parameters, we claim that our phase transformation pressure is, let's say, 1.3 GPa, right? But then when we do phase field modeling, we apply this 1.3 GPa to our sample, which is full of dislocations, and local stresses at tip of dislocation pileup can be 60 GPa. And this is not only pressure, shear stresses. You know, problem is why macroscopic theory, macroscopic thermodynamics does not work. Because shear stress, macroscopic shear stress is limited by macroscopic yield strength. And this is several GPa. And its contribution in comparison with high pressure is small, tenths of percent. But at nanoscale, shear stresses are limited by theoretical shear strength, which is 1 to 2 orders of magnitude higher. So in addition to huge normal stresses, locally, we have large, huge shear stresses. And they satisfy our phase transformation criteria, which is not 1.3 GPa, which is about 60 GPa. So all what you said is exactly true, and that is what we take into account by multi-scale modeling. When I said reduction in pressure, that is average pressure which is applied to sample of size to point, material point of size of several micrometers. But within this micrometer, indeed, stresses in some region can be much higher. In others, they are lower, but average is like this. Very good point, and exactly to what I wanted to say.
Can I? One more question.
Okay.
Nice suggestion about the earthquakes. In your model, so earthquakes happen when stuff is going down, and it doesn't happen when stuff is coming up. Can you comment on that? It should also have earthquakes when stuff is coming up, according to your engineer.
No, it should not come up. And actually, during deep focus earthquake, nothing comes up or down. They are not as dangerous as shallow earthquakes. Yes, yes.
But you also have
Oh, you mean that is what you mean?
stuff going down and coming up. So
Well,
you don't see earthquakes when the stuff is coming up.
Well, point is that why it's important that it comes down. When it comes down, it's cold. Temperature is low. That is why olivine is metastable. It does not transform. If it would be at much higher temperature, it would transform much smoothly, let's say within hours, like in laboratory experiments. So key point why it's important that it comes down. When it comes down, it's cold. And that is why it does not transform for million years, despite the fact that it's already deeply in region of stability of spinel. But then plastic strain produces completely different type of phase transformation, plastic strain-induced phase transition, which we produce even at room temperature. If it would come up, it would be hot. And actually, if it comes up, it will start from Bridgmanite, right? Where it would transform to. So I think it's very important that subduction is very important part here, just to keep cold material.
Thank you. One influence you made was that the youth strength is being influenced the pressure, similar like
Yes. No, there is not always, but you know, even we feed data based on literature. We feed our modeling to literature data, for example, for tungsten, for molybdenum, and pressure up to 200 to 400 GPa. And we wanted badly to have quadratic term, but it's negligible.
And then what does B depend on?
Say it again.
What does B depend on that variation that we multiply?
Well, I don't know. This is just empirical parameter, and it's usually at the order of 0.1. I cannot say what determines this parameter because there are various factors which may affect this based on dislocation theory, elastic. First, one of explanation is increase in elastic properties, but it does not tell us entire story. Most important is a change in dislocation core structure, and it occurs even at quite low pressure. But there is no quantitative theory at the moment, and I did not focus on this to determine this parameter analytically, because too many, you know, too many possible reasons for this. Well, I cannot. People can. Yeah, we don't do shock loading, but now we started dynamic experiments with dynamic rotational diamond anvil cell, and we expect this is a rotation up to 4,000 rotation per minute, and evaluated strain rate is at 10 to 4 over second maximum.
The question is, like, how plastic deformation produce through dynamic shock
Yes,
and through this RDSE
yes.
will be different. Can we quantify deformation?
Well, I assume that it will be different because in shock you do have plastic deformation, but not severe plastic deformation. It's probably, well, unless you have shear bending. If you have shear bending, I don't expect any difference. But time appears as parameter. And I did not discuss one of slides actually, even in when we did more detailed experiments, time also appears as parameter. If after torsion or after compression, we keep without additional compression and measure time evolution, nobody did this before. It progresses, so volume fraction increases by 20–30%. So actually, even in our case, time should be included. We will work on this. Bianca wanted badly long time.
Doesn't mean, oh. I have just a brief comment.
Yeah.
I don't want to blame you, and you know, I know all literature sometimes gets lost.
Yeah.
But we still want to honor our older colleagues. Bill Bassett, some 20 years ago, converted polyene to spinel into shear powder.
I know this. I know this, yeah. And it was with Pam Burnley. It's a joint work. I know this. Yes, but again, this was a single paper, and after this work was not continued. It was at high, not only at high pressure, but it was at high temperature, and it was during several hours. And we are doing this at room temperature and within tenths of second. I cite, of course, this paper in my publication, so I try to honor.
Thank you for a very interesting talk. Is there some critical analysis for the transition? Is it possible to somehow define the analysis during the formation?
Well, you know, at different scales, criterion looks differently. I don't use concept of critical energy here, just a combination of, for example, for you're talking for probably perfect crystal, or you're talking about real material. If for perfect crystal, I'm talking about combination of all components of stress tensor, which cause phase transformation. We can introduce generalized Gibbs energy, but it's not very clean. So there are problems. It depends on path for large strain formulation. That is why I try to avoid this. We have this in papers, but it's more straightforward to use combination of stresses.
This concept of energy, the result in what we call the steady state, no?
No, steady state, it's not related to energy. It's steady state, I would say, in dissipation. This is more like, you know, there was theory by Prigozhin, let's say, Prigozhin theory of steady state behavior of strongly nonlinear, non-equilibrium system. So because this is what happens under severe plastic deformation. Energy stays steady, but this is not important. Important that microstructure remains steady, yield strength remains steady, minimum pressure for phase transition does not change anymore. I would not connect this to energy. It's more for theory of dissipative systems than just driven by energy.
First thing that you got on the silicon, I mean, it's very.
Same thing.
Have you started playing with germanium where you have even more better stable cases you could potentially access it?
No, we did not. We wanted, we did not get this project because they said that the germanium is similar to silicon. And well, I believe that just study silicon under all these conditions, you need several lives, and germanium is different. But you know, money decide differently.
But let's take let's begin again.
Thank you.
But for some small